Okay, so when we're looking at an independent t-test, if the null hypothesis is rejected, we're saying the mean of one sample is so far from the other mean that the samples likely come from populations with different means. And this is a bit complicated to explain what this really means, but let's say that um, we're looking at males and females and difference in attitude towards math. We have some kind of scale that shows attitude towards math. Um, what we really want to know is, does it matter if you're male or female when it comes to your attitude for math? So say we get 100 males, 100 females, and the male average is, say, 5.6 on a scale of 1 to 10, where 10 is very anxious. Females is 3.4. I think the reality is actually switched in the math ed literature, but if those two are different enough based on the t-test, the independent t-test, then we're saying that, yeah, males and females are really two different populations. Okay, now when would you conduct an independent t-test? So most of you most of you had the correct answer, but the greatest wrong answer was that none of these was suitable. So let's just talk about the correct answer here. When we're looking at a memory study, so one group does alphabetical order and the other memorizes the words from shortest to longest. We have two separate groups. It's not like husband and wife are paired and one's in each group. There's no pairing going on, and there's no pre-test, post-test, which is why it's an independent t-test. Independent t-test means all we do with our one group is just get an average for it. In our second group, we just get an average for that, and then we compare the two means through some kind of calculations, which I have not stressed in this course. But the point is, we're not making a one-to-one correspond. In fact, we could have 30 people in this group and 25 in this group. That's no big deal in an independent t-test. In a dependent t-test or a paired t-test, you do need to have exactly the same number because there needs to be an exact pairing going on. Okay, so we got our alpha significance level is 0.01. We get a 0.001, and I think you got the fact that 0.001 is less than 0.01. The question is then, what do you do? Do you fail to reject the null, or do you reject the null? Well, if your p-value is lower than the significance level, this is the cutoff that we have to get. So if it's lower, this alpha level of 0.01, ours is lower, so then we do reject. If our p-value that we get is lower than the significance level cutoff, then we do reject the null. So that is the correct answer. Okay, p greater than 0.05. Similarly, if our level of significance 0.05, the cutoff is 0.05, and the researcher got above that, that means, go back and read the definition of the p-value. It's basically, if the null hypothesis is true, this is the percent chance that we would get results this extreme just by chance. So if we're greater than 0.05, we're saying, yeah, okay, it could have happened by chance, but it could be the null hypothesis, could be that the research hypothesis is true. We just don't have enough evidence. Whereas if we're less than 0.05, we're so far away from that null hypothesis that we're going to take a step and say, okay, we're rejecting this null hypothesis. We're too far away. The chance is so slim, it's less than 5%. That was not the case in this article. P was 0.05. It was above the cutoff level of significance, so we fail to reject the null. Notice that we don't accept the null. So we don't really know that the two are the same. We don't know that the null hypothesis is true, but we don't have any real strong evidence to reject the null hypothesis. So that's why it's reject or fail to reject. It's never accept the null. Okay, z-score is basically how many standard deviations are you in comparison with the mean? How many are you above the mean? So if you're -3 z-score, it means you're 3 standard deviations below the mean. Mean is 12. Each standard deviation is 2, but Jack is 3 of those below. So 3 2s is 6. So 12 minus 6 would be 6 actual score. Okay, the other popular answer there was 9. So 9 would be if he was, if the standard deviation was 1, and then he was 3 of those 1s below 12, that would give us a 9. But because the standard deviation is 2, and the z-score is the number of standard deviations away from the mean, we know that he was 6 below the mean of 12. In other words, he had 6. Okay, 95% and 99%, which will be shorter. So think about if you say, I'm 99% sure, blah, 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 versus I'm 95% sure, blah, blah, blah. So 95% sure, you can have a little more, you have less certainty, so you can have a little more precision on what the exact answer is. So we're 95% sure that this political survey is within a 2% of the correct population mean. But 99% sure, you need a bigger basket to catch all the possibilities if you're going to be that sure about something. So we're 95% sure we're within 2 percentage points. We're 99% sure that we're within 5 percentage points. There's not very much chance at all that we're going to be outside of the 5, whereas there's a little more chance that we could be outside of that 2%. So that 95% will be shorter because we can be more precise when we're less confident. Okay. So again, a null hypothesis, if our sample mean is outside of the 95% of all possible means where we assume it's true. This is just another way of saying that we're less than 5%. Our p-value is less than 0.05. So I'm trying to drive this point home in several different ways, which I know is annoying to some people on the test, but hopefully that reinforces the idea that this is an important thing, understanding what this p-value actually is. So I'm trying to restate it in several different ways. So if our alpha level or significance level is 0.05, then anything that's outside of the 95% of centra values, anything that's way out in these tails, these extremes, that's when we reject the null. Okay, so this was an interesting question, and again, I would defend this question as being important to know. So we want to know which of these was an experiment. Well, what is an experiment? An experiment is where we let everything randomize. That's why we have this random assignment, except for one thing. And that one thing is our treatment. But the issue, because we're randomly assigning people to the treatment, we have to make sure that each person could be in that treatment. For example, if we look at prior reading attitude, and if I have a sample and I divide it into 3 groups, I can't tell these people you have to have a high prior reading attitude. You have to really enjoy reading. and this group you have to hate reading, because that's not realistic. I don't have control over that variable. Similarly, socioeconomic status. When I randomly assign people to the different groups, I can't tell them, okay, now you guys are going to be high socioeconomic status, because that's some kind of status that's already decided on them. Incidentally, even if I were to give one group lots and lots of money, that's only the economic part. It's not the socio part, which is part of socioeconomic status. So I can't control that variable. Gender, as far as I know, there's no way to control. Maybe through some extreme hormone, but that would be very extreme, and obviously not in looking at elementary students' attitude toward reading. Reading comprehension, again, I can't control any of these four things. Only in study A can I control the type of material. I can say, this group, you're going to be reading fiction for the experiment. This group, you're going to be reading nonfiction. I have control over that. So A is a potential experiment. Okay, we have pre and post test. So this is a dependent. We have the same number of pre and post scores. And let's say that someone drops out of the study, we have to throw their pre-test out because we need the same amount of pre-test and post-test, and there's a way to pair them. You're going to match my pre-test with my post-test, Susie's pre-test with Susie's post-test. You don't match my pre-test with Susie's post-test. So this matching, one thing it does, it gets out of a lot of the extraneous variables that might be related to me or to Susie. So that's the purpose of doing a dependent t-test. But the simple thing here is a dependent t-test is what you use with a pre and post. And then what you end up doing is you subtract them to see the difference between the two. So this kind of gets into the value added that you've probably heard a lot about, for better or worse. Okay, ninth percentile. We can do this many different ways. One way would be to look at the normal distribution. We know that 95% are within 2 standard deviations, so negative 2 z-score and positive 2 z-score would be 95%. Any of these other answers, so less than 1% would be less than 1 standard deviation. We're not nearly far enough away from the mean. 68% of the data is going to be within one of the mean, and we're certainly not within that 68% that's lumped around the mean. So you could look it up on a table to get an exact answer, but we didn't emphasize this in the class. We only looked at kind of a general idea of what z-scores are, and so negative 1.34 is the only one of those 4 that's within the acceptable range. Okay, when a z-score is negative, what that means is a z-score is how many standard deviations you are above the mean. So if you have a negative, you have to be below the mean. A z-score of 0, you're exactly the mean. Z-score of negative 0.0001, you were below the mean. Just a little bit, but you were below the mean. So anytime you see a negative z-score, you're always below the mean, always less than the mean score. Okay, results of a descriptive study. So this gets at that correlation versus causation idea that I talked about in, I think, a couple videos. Descriptive study, it's very difficult to show that something causes something else, and certainly a descriptive study don't do it. In fact, most research studies cannot show causality. You either need a experiment, a true experiment, or some kind of causal comparative, carefully designed quantitative experiment to show this causal relationship. So in this sense, when you say that children were more likely to cooperate if they were opposite sex, we're saying that being opposite sex in the children in the family caused the cooperation, which is not true.